are the hints on what's going to be on the exam. So let's go to the regularly scheduled session here and see what questions you have. Okay, someone asked about the grade distribution. Yes, I'll deal with that. Linked list. Is the linked list singly list or is it doubly linked? Let me look at the question here. I don't remember. This is homework. Oh, the other thing that you probably want to copy onto your local hard disk is all the solutions. Right? The solutions are all available to you, and so if you felt that any of that code was useful during the exam, have at it. So just in general, any code that I gave you in any form or shape, you can reuse for anything you want. So if I gave you a solution and it might help you, by all means, go for it. All right. Let me understand here really quickly what this question was. Okay, this is actually a better question than I at first thought. When I said to our linked list class, the intent was that it was the one in section 16.1. This is for problem 8b. And let's see for problem 8c. Yes, also problem 8b and 8c. And so the source code is now in Desire to Learn. There's minute differences between the implementation in your paper book versus the ones in the PDFs. They're not going to matter much for either of these two assignments, but I think the straightforward thing is just take the one in section 16.1 in Desire to Learn, in the zip file in Desire to Learn. So it's in the content area. And you should be happy with that. So both of the times they are singly linked. You're not going to get much advantage out of a doubly linked. The first one was the one where you need to reverse, where you need to reverse the links. There's no advantage of using the doubly linked. You just have more links to reverse, so don't use the doubly linked. The second one is where you need to compute the size by just hopping the links. The reverse links don't do anything for you. You wouldn't even look at them. So just use the singly linked in both cases. Okay, next, in data from lab 6 are declared as variables but are called as methods. I don't mean them to be called as methods. If I did, that would be a typo in the lab. What I meant is, and what I thought I had in the code is, so you have this class linked list public, and inside that we have a class node and it has two public fields, and they're just fields, so they're not methods. And then somewhere else in the linked list code you might say something like first dot next equals dot dot dot. And so notice there are no parentheses here. So it doesn't say dot next with the parentheses. It just says dot next without parentheses. And so it's not a method that we're accessing. We're directly accessing the field of this object. Now at the beginning of last semester, they told you that it is evil to access a field directly. They're private fields. You should always go through the public interface. And so here we seem to be kind of violating that, but that's why this class is an inner class. Only the linked list class knows about it, and it's very tightly linked to, connected with the linked list. And so in this setting, it makes sense to bend the rules a little bit and to say it is perfectly legitimate to access fields directly as long as they belong to a private inner class. Now, no one in the public would be able to do this anyway, and that way the code gets a little bit simpler. We don't have to say like first.setNext and first.getNext. It just keeps the code a little bit simpler, and it doesn't really give anyone else any way of manipulating our linked lists in any evil way. So they're not methods. Now, it's possible that when I wrote up the lab that somewhere I accidentally put in the parentheses. In that case, you would need to let me know where, and I'll fix the typo. But I didn't mean you to access any methods. And so this is important that as you monkey around with these linked lists, if you have the situation, let's say you wanted to swap these two nodes, for whatever reason, I make you swap these two nodes, right? Where you then would say, okay, that means that this one here goes here, and then this one here goes. Oh God, this would be a mess. I'm not making you do that on the exam. And anyway, I was wrong. This one here doesn't get moved. Then you would have to be able to draw a diagram like that and read off something that says first dot next equals first dot next dot next. And each of those, first dot next, we're accessing, we're poking right into the node objects. So make sure you have a close look at that as you do. Particularly today's lab is going to have be full of things like that. All right. So let's hope that explained that. If not, ask another question about this. See, then we had an unresolved follow-up here. Ooh. Yes. Take out the static. Good call. I'll take that out of the description. That is that whole thing with static versus non-static inner classes is a tricky business, and I'll see if I can give you some online reference for those of you who are interested. But if I discuss it in class, I know I'm going to be losing a good number of people. It is very technical. But you're absolutely right. That static isn't going to work. I had not thought of that. The other option would have been to make node a static inner class, and I didn't want to do that because it's just confusing. Okay, excellent. So let's go on with the lecture. So let me actually go back to the end of last lecture. If I remember correctly, I kind of did a sloppy job there at the end with the efficiency of remove. So the issue here was, why is removing the last element, why is it O of n? Why is adding O of 1? And so it's a little confusing because for the efficiency of adding to the n to be O of 1, I have to have a reference to the last element. So in my linked list, I have to have a first and a last. And then the last will go like this. Now, the code in the book didn't have that for simplicity. Or did it? I don't even remember. Let me look it up before I say something wrong. No, I'll look it up in a minute. I don't want to ruin my picture here. So we have the reference to the first and the last. And now to add past the end, how do you do it? You follow the pointer to the last. That gives you this node here. Then you can add a new node here. and then you can move this one to the new node that you just added. O of 1. Fixed number of steps, doesn't matter how long the list is. I didn't have to traverse this one. And now I was really muddled last time about why is it not, what about removing the last one? And so here goes. So now I have this picture here. And now I want to remove the last one. Well, it's easy enough for me to find the last one because I just follow this pointer here. And then finding the last one. Just takes one step. But how can I remove it? To remove it, I would need to be able to take this thing here and change it to null. That reference now needs to become null, but I don't know how to get at it. I don't have a reference to the preceding one. I don't have a link that goes the other way around. I can, of course, get at it by going at the beginning and making n-1 hops. Then I have it, and that's my O of n algorithm, but I can't do any better than that because I didn't remember the previous one. So that's why removing the last element in a singly linked list is going to be O of n. And where I got myself confused last time was I was thinking about, well, what if I have an iterator to the last element? Because even in a singly linked list, if I have a list iterator, the iterator does remember the previous one. I'm sorry. So we have the previous and the current one. So the iterator does have a pointer to the previous one and to the current one. And yes, indeed, because the iterator remembers the previous one, I would now have all of the information to do removal. I can say, well, I have the previous one, I can store it in the last, and I can set the previous next ones to null. But how am I going to get myself that iterator? The only way that I can get it is to ask the linked list, give me an iterator, please, and then move it n-1 steps so that it is just before the last one. And that's, again, O of n. So one way or another, removing the last element from a linked list is an O of n operation. I can directly, without an iterator, go to the next link in a loop n-1 times, or I can use the list iterator and move it n-1 times so that it's at the last one, and then I could do the removal. But only after I have done those n-1 steps can I do it. Can I do the removal quickly? All right. So that's what I messed up last time. Let's now go back to today's lecture. All right, so the topic today is doubly linked lists. And so I know it's technical and boring, but it's a useful skill to have to deal with these. So in a doubly linked list, every node has a link to the predecessor. And we always store a tail reference. So we now have reference to the first and the last. So let's look at how we would need to change the code from singly linked list to doubly linked list. Here's the code for the singly linked list. So in the singly linked list, to remove the first, I first check whether there was one and otherwise throw an exception. Then I fish out what was stored in the first because I need to return it. Remove returns the object that was there. Then I change this link to the next. So if I draw that picture real quick here. So here's the first. So I want to get rid of this one, and so I have to move this one to be over here. And finally, I return the thing that I removed. All right. What do I need to do to make this work for doubly linked lists? Huh? All right, so let's see. 1, nothing. Well, that can't be true, right? Let's actually see in this picture here what we would have to change. So I want to get rid of this one here. So I'm already in the code that you've seen. I'm already doing this motion here. But surely I must do something to this previous here. I must put a null in here. Because otherwise, if one were to navigate backwards, you would find yourself in now deleted territory. So we need to put that null in here. And now let's see. Update the previous reference of the initial node after removal. That could be a good answer depending on what do you think is the initial node. Is this thing the initial node? Well, this one I don't have to change it to null. Is this one the initial node? Yes, I do have to change it to null. So that might be a good answer. Now let's see. Update the last reference of the linked list if the last element was removed. Do I have to update the last reference? Well, let's see what the popular opinion was. Interestingly enough, 9 people said yes. And I'm going to say yes too. And here is why. And that's generally a tricky thing when you deal with these kinds of situations. Suppose my list had been the following. Here's my linked list. Here's my node. That's a perfectly legitimate linked list. It's a linked list that happens to have one element. Right? You can't rule it out. It can happen. And now, when we look at the code here, so in this case, it would set first to first.next. So let's see what that would do. First.next is here. That's a null. And previous is also a null, of course. And so first equals first.next will work beautifully. It'll now make first into a null, which is what we want it to be, because an empty list has null as first. But we also need to change last, right? Because we also want this to be null. And there's nothing in our code over here that touches last. So C is totally correct. And so there must be so we must have a case for that. So 2 is also kind of correct. So the correct answer would be 2 or 3, or for that matter 4, if you felt that something else means both 2 and 3. All right, so this one here doesn't have a correct, it does have a wrong answer. Number 1 was definitely wrong. So those 2 people who said nothing, rethink on, no. That one person who said nothing. No, no one said nothing. Great. Oh, great. Oh, we're good. All right. So, just think this through. It is generally speaking, you really have to think through these things carefully. And so you see myself that every time I draw these diagrams, because without having that diagram in front of you, I don't see how you can solve these problems. I wouldn't be able to do it. And I've been doing this for many years. When you have these links that go, there's all these links floating around. If I don't draw the picture, I'm totally lost. So I want to draw that picture every single time. And now I also realize when you see me drawing that picture and those links go fast and furious, you're saying, well, what the heck is he doing? The only way that you're going to figure out what the heck I'm doing is if you draw those pictures yourself. You have to do it. I vividly remember when I learned this material for the first time when I was an undergraduate. I had no idea what the professor was doing at the board. I still remember that. Until I got out my pencil and started doing the stuff myself. And after several hours of suffering, I finally figured it out. But this is something you really have to do with your own brain. All right, so here we have to do both of these things. We have to say, if first is null, then we have to set last is null. And otherwise, we need to reset what now is what's the previous of the now initial one also to null. Okay, adding at head. So this was what we did in the singly linked case. Do we have a quick? Yes, we do. Huh. So let's set this one up. Okay, I'm just going to draw the picture again. You should draw the picture. No, I don't want that. No. First. Last. Next. previous. Now I'm going to insert a new one. It's this one here. First, next one needs to go here. Previous one needs to go here. And what code do we have? What are options? Okay, I need more answers. So the question is, which of these steps have not already been done?
Can you bring the choices back?
Yeah. I don't know how to do both. So if you look at the diagram here, I did rerouted 3 links. I said the first needs to be rerouted to the new node. That's here. Let's see if we're doing that already. Where's my code? Here. And we're doing that here. No. First equals new node. What am I saying? Yeah, we're doing it here. Then I said, this guy here, the new node.next needs to point to where first used to point, and we're also doing that. That's here. And then I said what now is the second one, its previous needs to point to what now is the first one, and that one couldn't possibly have been done before because previously we had a singly linked list that didn't have a previous. So for sure, this thing here has to be a part of the answer. So that rules out 1. We have to do something. It validates that 2 does need to be done. But unfortunately, choice 4 says both 2 and 3, so we do have to think about 3. Update the last reference. Why the last reference? It's add first, not add last. We're never going to add to the last in add first. Or are we? Yes? Very good. What if the list was empty? Right? In that case, the first and the last are the same thing. And so that's exactly the right thinking here. So what if at the outset the list was completely empty and naked and had no element in it at all? In that case, now here's our list. And it has a null in here and a null in here. Sorry about my sloppy nulls here. So now what do we have to do? We allocate a new element in bright orange. It's a little known fact of life that new elements are orange. No, I think they're this orange. So that we can actually see them. Yes. Okay. So we have to set first to it. We have to set last to it. Right? We really do need to do both of those steps. And so the correct answer is 4. So let's see how people did. And yes, so most people got it. Great. All right. So here's the code. If first equals null, that means we have an empty list. Then we make sure to set last, and otherwise we set first.previous to new node. You need to follow that along in the picture to see that that's really the right code. All right. Adding at the tail, I'm not giving you the code here, and what I want you to pay attention to is that this doubly linked list is highly symmetric. That you have a pointer to the first, you have a pointer to the last, you have the next and previous that are exactly opposite to each other. And so the way that I wrote add last was literally, I took add first, copied and pasted it, and changed all the firsts and lasts, all the previous and nexts. And because it's such a symmetric arrangement, that simply had to be the right thing. The same thing with remove last and get last. If you can do the first, you can do the last. All right, now on to the iterator. So first of all, the bidirectional iterator has to have a previous method so that you can go to the linked list from the beginning to the end and then back from the end to the beginning if so you choose. That's what you can do in a doubly linked list. And there's a little bit of funniness about previous and because these iterators, if you remember, they sit conceptually between elements. So in this case here, you have these elements A, B, and C. And so the iterator starts out before the first. Now when you call next, it skips over the first and returns an A. And then when you call next, it skips over the B and it returns a B. Now when you call previous, then it skips over the B again, and it also returns it. It always returns what it skips over. And so one just has to remember that when you go backwards, then it returns the element that was to its left, so to speak. All right, so one just has to remember that. It's okay. Remove, on the other hand, is not so much fun. The contract for remove says it removes the element that was just skipped over. And so for the implementer, this is terrible because you now have to remember, next is not so bad. You implement next and you figure out what element you traversed and you just return it. But with remove, your iterator has to have long-term memory. It has to remember, did I just move to the left or did I just move to the right? And this is very unique to the Java library, that if you look at how it's done in C++, for example, you don't have this stateful nature. And it's a total design mistake. Every time that I try to explain to a student how remove works, their eyes just glaze over, just like yours. So the reason they did it like this was they wanted to have what seems at first glance to be a desirable property of remove. They wanted us to be able to write the following loop where we iterate through a linked list while there's still a next. Then we want to call iter.next. We want to check whether it has a particular property. And if that's the case, then we want to call remove to remove the thing that we have just found to have that property. And now we want the same thing when we iterate backwards. And I guess that sounds kind of like a good idea. But it does really get confusing if you move away from this pattern at all. With this pattern, it works beautifully. As soon as you move away from that pattern, it gets very confusing what remove does. And the problem with it from an API design, which is why I want to point it out in case you ever need to design an API. The problem with this is that iter.next does two unrelated things. And so it's the same thing with iter.previous. Number one, it moves the iterator to the next of the previous position. Nothing wrong with that. Number two, it returns a value. And that's actually bad design. The general rule is that if you have a mutating operation, and next and previous are mutating, they mutate the iterator. The iterator is now at a different spot than where it was before. When you have a mutating operation, you don't also want to return a value. And so they violated this rule of API design. So generally, when you design your own API, think of separating the mutators and the accessors and make it so that the mutators return void and the accessors return information. That's what is an accessor. So in C++, for example, this is done right. One separates the movement of the iterator from inquiring what's under the iterator, or rather in C++ you would say what's to the left, what's to the right, because after all the iterator is between. And you can ask that as often as you like without having to move the iterator. Mixing, moving, and inquiry is bad. Anyway, we have to deal with the API that has been handed to us. And so when we want to implement it, we need to implement that. So the way I implemented it is I have these two flags where I remember whether it's after next or after previous or neither, in which case they might both be false. Because remember, when you call previous and then you call remove, then you're not allowed to call remove again. I tell you, it's a crazy API. So I remember that. The only thing that can't ever be true is after next and is after previous can't both be true. But you could have true false, false true, and false false. So here are these flags. So I'm not going to go into this, but will I go into remove? Yes, I will briefly go into remove because it's in the lab. So there's a helper method to find out what to remove, and it just checks whether you had is after next and is after previous. And why the heck is there this extra case? Oh, yes. So, do I want to do this? Sure, in the interest of punishment. So here's my linked list, node, next, previous. And so there is a tricky situation when I have the list iterator, and it was on this element, which really means it was after this element, because it conceptually sits between elements. And now I call previous on the thing. What happens? Then it moves to the predecessor, which is null. So it actually points to null. And that is the state of the iterator when you are before the first element. So in this case, which element do I need to remove? I need to remove the one, well, I need to remove this one here. But I can't use the position because the position points to null. But fortunately, that's the first element in the list. So I can just return first here. All right, that's enough. So let's now deal with the situation. How do we reroute the links around it? Do I have a picture of this? You're going to be drawing that picture in the lab, so I don't have to do it. All right, so I just want to very briefly talk about testing. I'm not going to have time to do this right now, but it's something that happens in the lab. As you notice with these kinds of methods here, what is the chance of getting this correct the first time around? Give me a percentage. What is the chance of implementing this correctly the first time around? 0. You're going to do something wrong, right? I did so many things wrong when I implemented this, and this is the 3rd or 4th time that I did this in my life. There's so many fiddly details. And so the only way to deal with something like this is to write an exhaustive set of tests. And I know this is the hard way because in, I think, the second edition of this book, I forgot some case. And I got so many complaints from instructors who used the book, and where some smart student said, in this particular situation, that if you first, add all of these elements, and then the iterator runs all the way to the end, and then runs one step backward, and then you have full moon, then something bad happens. And it really was like that. And it was very embarrassing. So I learned that what you need to do is you need to just really write a lot of test cases to make sure that you cover all of these fiddly little things. Empty lists, non-empty lists, lists that have one element, that have two elements, that have lots of elements. So this is where JUnit really comes in handy. Unfortunately, in the book I wasn't allowed to use JUnit because not everyone who uses the book wants their students to learn it. So I did a kind of JUnit-like set of test cases in the worked example, but it's easy enough to translate them to straight JUnit, that instead of having that long method that you find in the book, just chop them up into individual methods and tag them each with add test. And now the test that you saw in the book is kind of interesting, and I'm not sure it's the right way of doing it, but I wanted to point it out. In the next chapter I have one that does it the other way around. When testing the linked list here, I'm only using the public API. So you would think that to test a linked list, what you pretty much have to do is to have helper functions right in the linked list that follow all those private links. But just to show that it can be done, I'm not doing that. So what I'm doing is I'm attaching an iterator, and I'm going from the front to the back, and then I'm going from the back to the front, and I'm checking that all of the elements that I expect to be there are in there. And I'm also checking that the first and the last one, as reported by get first, get last, are the correct ones. So that's that check. That's a bit more extensive than the checks that you have to do in the lab. But I thought that would be interesting for you to just have a quick peek at it. All right, so let's move on to the lab without much further ado. So I don't know how far you got. Pick up where you were, and I'll make the round and see how far you did get. So we'll do the lab today and for sure on Thursday because, it's a long and complex lab. And yeah, that's it.